Section 5 of National Geographic Magazine, Volume 1, Number 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Report, Geography of the Sea, Part 1 by George L. Dyer. In presenting to the National Geographic Society this first annual summary of work accomplished in the domain of the geography of the sea, I find it impossible satisfactorily to limit the range of subjects that may be assigned to it. The great ocean is so large a factor in the operation of nature that the attempt to describe one of its features speedily involves the consideration of others lying more or less in that shadowy region which may be claimed with equal force by other sections of the society. It is to be understood, therefore, that the following account merely touches upon several of the characteristics of the oceanic waters, and is not in any sense an attempt to treat them all. This being the first report to the Society, it has been thought advisable to give a brief outline of the progress made in our knowledge of the sea since 1749, when Ellis reported depths of 650 and 891 fathoms off the northwest coast of Africa. Even at that time, an apparatus was employed to lift water from different depths in order to ascertain its temperature. It does not appear that this achievement gave impetus to further efforts in this direction, for, except some comparatively small depths and a few temperatures recorded by Cook and Forster in their voyage around the world in 1772 to 1775, and in 1773 by Phipps in the Arctic, at the close of the last century there was but little known of the physical conditions of the sea. At the beginning of the present century, however, more activity was shown by several governments, and expeditions sent out by France, England, and Russia in various directions began to lay the foundation of the science of oceanography. Exploration of little-known regions was the main purpose of most of these expeditions, but attention was paid also to the observation and investigation of oceanic conditions, so that accounts of soundings, temperatures of seawater at various depths, its salinity and specific gravity, the drift of currents, etc., form part of their records. The first to give us a glimpse of the character of the bottom at great depths was Sir John Ross, the famous Arctic explorer. While sounding in Pond's Inlet, Baffin Bay, in 1819, by means of an ingeniously constructed contrivance called a deep-sea clam, he succeeded in detaching and bringing up portions of the bottom from depths as great as 1,000 fathoms. The fact that this mud contained living organisms was the first proof of life at depths where it was thought impossible for it to exist. The truth of this discovery, however, was not generally accepted, many eminent men of science on both sides of the Atlantic contending for and against it, and the question was not fully settled until long afterward, in 1860, when by the raising of a broken telegraph cable in the Mediterranean, unimpeachable evidence of the existence of life at the greatest depths in that sea was obtained. The science, however, remained in its infancy until about 1850, when Maury originated his system of collecting observations from all parts of the globe, and by his indomitable energy aroused the interest of the whole civilized world in the investigation of the physical phenomena of the sea. Through Maury's efforts, the United States government issued an invitation for a maritime conference, which was held in Brussels in 1853, and attended by representatives of the governments of Belgium, Denmark, France, Great Britain, Netherlands, Norway, Portugal, Russia, Sweden, and the United States. The main object of the conference? To devise a uniform system of meteorological observations and records, was accomplished. According to the agreement, ships' logs were to have columns for recording observations of the following subjects: latitude, longitude, magnetic variation, direction and velocity of currents, direction and force of wind, serenity of the sky, fog, rain, snow and hail, state of the sea, specific gravity and temperature of the water at surface and at different depths. It was also proposed that deep-sea soundings should be taken on all favorable occasions, and that all other phenomena such as hurricanes, typhoons, tornadoes, waterspouts, whirlwinds, tide rips, red fog, showers of dust, shooting stars, halos, rainbows, aurora borealis, meteors, etc., should be carefully described, and tidal observations made when practicable. The practical results of this conference were great. The systematic and uniform collection of data by men of all nations is going on uninterruptedly today and is furnishing the means for the solution of many of the problems relating to the geography of the sea. An epoch in the progress of this science is marked by the appearance of Maury's wind and current charts, his physical geography of the sea, and his sailing directions, which contain the record of the first deep soundings taken by United States vessels. And to the United States, through Maury's efforts, belongs the honor of having inaugurated the first regular cruise for the purpose of sounding in great depths. Under the instructions of Maury, the U.S. brig Dolphin, commanded by Lieutenant Lee and subsequently by Lieutenant Berryman, was detailed in 1851 to 1853 to search for reported dangers in the Atlantic and to sound regularly at intervals of 200 miles going and returning. The Dolphin was provided with Midshipman Brooks' sounding apparatus and with it succeeded in obtaining specimens of the bottom from depths of 2,000 fathoms. About the same period, the U.S. ships Albany, Plymouth, Congress, John Adams, Susquehanna, St. Louis, and Saranac also made soundings in various localities, and to the USS Portsmouth in 1853 belongs the honor of having reported the first really deep sounding obtained in the Pacific, 2,850 fathoms, in about 39 degrees 40 minutes north and 139 degrees 26 minutes west. The practicability of this work was thus fully demonstrated, and, although some of the earlier results, through defective appliances and lack of experience, were not entirely trustworthy, its character and success will always be a tribute to American enterprise and ingenuity. With the advent of the submarine telegraph, the investigation of the depth and configuration of the ocean bed became of vital importance, and the work of sounding for that purpose was taken up with activity. One of the first voyages in the interest of these projects was that of the USS Arctic under the command of Lieutenant O.H. Berryman in 1856 between St. John's, Newfoundland, and Valentia, Ireland. The Civil War naturally put a stop to these operations by United States ships. The U.S. schooner Fenimore Cooper was about the last engaged in this work, sounding in 1858 to 1859 in the Pacific to 3,400 fathoms, and also reporting a sounding of 900 fathoms only 3/4 of a mile west of Gaspar Rico Reef in about 14 degrees 41 minutes north and 168 degrees 56 minutes east. The work so well begun by the Americans was quickly taken up by other governments, and we find from that time to the present the records of a large number of expeditions for diverse scientific observations in all parts of the world. Continued improvements in the appliances and instruments have made the results more precise than was possible in the earlier times, and, as the data accumulate, the bathymetric charts of the oceans are becoming more accurate. Not until this work is much further advanced, however, shall we be able to arrive at an estimate of the depths and weights of the oceans at all comparable to our knowledge of the heights and weights of the various great land masses above sea level. Other important results of these expeditions have been the verification of many reported elevations of the ocean bed formerly considered doubtful, the discovery of new ones, and proof of the non-existence of others, which had been reported as dangers to navigation. The geography of the sea reached a decidedly more advanced stage by the inception of several great scientific expeditions, of which that of the Lightning in 1868 to the Hebrides and Faroe Islands under the superintendence of Professors Carpenter and Wyville Thomson was the forerunner. This was followed by the 3 years' cruise of the Challenger, British, in 1873 to 1875, the Tuscarora, American, in 1874, and the Gazelle, German, in 1875, by those dispatched under the authority of the U.S. Coast Survey and of the U.S. Fish Commission, and others of lesser importance sent out under the auspices of European governments and by private individuals. All of these have contributed in an eminent degree to the progress of the science by giving us a better understanding of the physical and biological conditions of the sea at all depths. Special mention must be made of the splendid work that is being done continually by the expeditions sent out by the U.S. Fish Commission. This branch of the United States Service, originally established for the investigation of the causes of the decrease in the supply of useful food fishes and of the various factors entering into that problem, in pursuance of these objects has been prosecuting a detailed inquiry embracing deep-sea soundings and dredging, observation of temperatures at different depths, transparency, density and chemical composition of seawater, investigation of surface and undercurrents, etc. In other words, making a complete exploration of the physical, natural, and economic features of the sea, besides collecting a large number of specimens of natural history. The expeditions sent out by this commission have brought to light from the deep beds of the ocean an extraordinary variety of animal life, previously unknown to science. Few vessels have furnished a greater number of deep-sea soundings than the FCS Albatross. This steamer has explored fishing grounds on the east and west coasts of the continent, and since the beginning of last year has made a cruise from the North to the South Atlantic, along the east coast of South America, through the Magellan Strait, and northward along the west coast to Panama and the Galapagos Islands, and thence to San Francisco and Alaska. The scenes of her latest operations have been the plateau between the Alaskan coast and Unalaska and the banks off San Diego, California. A large share in the progressive state of the science of the geography of the sea must also be credited to the systematic collection of marine observations by the hydrographic offices and other institutions all over the world. This forms the stock from which, as I have already indicated, must be drawn, through intelligent reduction and deduction, a better knowledge of the intricate laws governing the various phenomena of the sea and air. Oceanic circulation. The existence of currents in certain localities was known at a very early date, and navigators in their voyages to the New World soon discovered the Gulf Stream and other currents of the Atlantic. The first current charts were published more than 200 years ago. Theories were soon advanced to explain the causes. One group of scientific men attributing the origin of currents to differences of level produced by an unequal distribution of atmospheric pressure over the oceans, another set connecting the tidal phenomenon with the cause of ocean currents, and still another finding in the rotation of the earth a sufficient reason for their existence. The polar origin of the cold deep water found in low latitudes has long been considered probable, and has given rise to a theory of a general oceanic circulation in a vertical and horizontal direction, produced by differences of temperature and density. Recent theoretical investigations, however, seem to indicate that these causes alone are incapable of producing currents, and today, the theory that the winds are mainly responsible for all current movements very largely predominates. Benjamin Franklin was probably the first who recognized in the trade winds the cause of the westerly set in the tropics, and Rennell soon after made the division of drift and stream currents. The objections which have appeared against the wind theory have been met with the reply that the present state of oceanic movements is the result of the work done by the winds in countless thousands of years. Current phenomena is briefly summarized as follows by one of the latest authorities on the subject. 1. The greater portion of the current movement of the ocean must be regarded as a drift, produced by the prevailing winds, whose mean direction and force are the measures for the mean set and velocity of the current. 2. Another group of currents, and in fact a fraction of all currents, consists of compensating or supply streams, created by the necessity of replacing the drifted water in the windward portion of the drift region. 3. A third group results from drifts deflected by the configuration of the coasts. These, which are denominated free currents, quickly pass into compensating streams. 4. The deflecting force of the rotation of the earth is considered as of subordinate importance, but may have some influence on currents that are wholly or in part compensating or free. Late investigations of the Gulf Stream by the U.S. Coast Survey give interesting facts in regard to that notable current. A satisfactory explanation of the cause of the stream has not yet been found, but many believe, with Franklin, that the powerful trade drift entering the Gulf of Mexico through the broad channel between Yucatan and Cuba presses the water as a strong current through Florida Strait, where the stream is turned to the northward along the coast. Since 1850, American naval officers have added greatly to our knowledge of the characteristics of this stream, particularly within the last decade, during which notable investigations have been carried on by Commanders Bartlett and Sigsbee and Lieutenant Pillsbury, U.S. Navy, under the direction of the U.S. Coast Survey, and by Lieutenant Commander Tanner, U.S. Navy, in the Fish Commission steamer Albatross. Of special importance are the valuable and interesting results in regard to tidal action in the stream obtained by Lieutenant Pillsbury, U.S. Navy, in the Coast Survey steamer Blake. From observations begun by him in 1885 at the narrowest part of Florida Strait between Fowey Rocks and Gun Cay, Bahamas, and continued since between Rebecca Shoal and Cuba, and between Yucatan and Cape San Antonio, Cuba, and off Cape Hatteras. During the past year, Lieutenant Pillsbury extended the field of operations to the passages between the islands encircling the Caribbean Sea, and in order to study the Atlantic flow outside the limits of the trade drift, a station was to have been occupied about 700 miles to the northeast of Barbados. This, however, was unfortunately prevented by bad weather. The deductions from the observations in Florida Strait showed very clearly a daily and a monthly variation in the velocity of the stream, the former having a range of 2½ knots and reaching a maximum on the average about 9 hours 9 minutes before and 3 hours 37 minutes after the moon's upper transit, and the monthly variation reaching its maximum about 2 days after the maximum declination of the moon. The variations in this section were found greater on the western than on the eastern side of the strait, and the axis of the stream, or position of strongest surface flow, was located by Lieutenant Pillsbury 11½ miles east of Fowey Rocks and further north about 17 miles east of Jupiter Light. The average surface current at this section was 3 3/5 knots, the maximum 5 1/4 knots, and the minimum 1 3/4 knots per hour. The results also indicate that when the current is at its maximum, the surface flow is faster than at any depth below it, but when at its minimum, the velocity at a depth of 15 fathoms or even down to 65 fathoms is greater than at the surface, and that there is at times a current running south along the bottom in all parts of the stream except on the extreme eastern side. The results of the investigations in 1887 and 1888 have not yet been published, but from information kindly furnished by the authorities of the Coast Survey, I am able to give a brief outline of the more prominent facts ascertained. In the section between Rebecca Shoal and Cuba, the daily variation in velocity was found as prominent as in Florida Strait. The mean time of 8 maxima corresponding to 9 hours 18 minutes before, and that of 3 maxima to 3 hours 25 minutes after the moon's transit. The axis of the stream in this section was found near the center of the current prism, and the flow was easterly and inclined on either side toward the axis. The axis seemed to occupy a higher level than other parts of the stream, and this appears to be borne out by the fact that about half the number of the current bottles thrown out in Florida Strait on the west side of the axis were recovered along the east coast of Florida, while of those thrown out east of the axis not a single one was heard from. As a rule, it was found that the stronger the current, the more constant the direction and the deeper the stratum. Remarkable fluctuations in the flow near the axis were noted, the velocity increasing sometimes 1 knot in 10 or 15 minutes, and then as suddenly decreasing again. Lieutenant Pillsbury attributes this, however, to a serpentine movement of the maximum flow which would sometimes strike the station occupied by the Blake. The edge of the stream was found at about 30 miles south of Rebecca Shoal Lighthouse. Between Yucatan and Cape San Antonio, the stream was found flowing about north, and the line of maximum velocity corresponds on the average to 10 hours before and to 2 hours 20 minutes after the moon's transit. The excessive variations were like those in Florida Strait on the west side of the stream, and the maximum velocity of 6 1/4 knots was found about 5 miles off the 100-fathom line of Yucatan Bank. The eastern edge of the stream lies about 20 miles west of Cape San Antonio, and between this edge and the island, eddy currents exist. At the time the easternmost station in this section was first occupied, the declination of the moon was low and the set of the surface current northeasterly. At a high south declination of the moon, the surface current was found southeasterly in direction and east or southeast below the surface. The normal flow below the surface was in each case from the Gulf into the Caribbean Sea, and this makes it probable that the station was situated inshore of the average limit of the stream. On Cape San Antonio Bank, the currents are tidal, flood running northward and ebb southward. On the Yucatan Bank, the currents were also tidal, but as the edge of the bank is approached, the stronger flow of the Gulf Stream predominates. The monthly variation in velocity, which was found clearly defined at the first two sections occupied, appeared at this section to be obliterated by anomalies not existing at the former. Off Cape Hatteras, the Blake accomplished the remarkable feat of remaining at anchor in 1,852 fathoms, and this with a surface current of over 4 knots. Two stations were occupied, and similar variations in velocity were observed as at the other stations. The notable feature at this station was the discovery of tidal action beneath the Gulf Stream, the currents at 200 fathoms depth changing their direction very regularly. The average current flowing about south-southeast 1/2 east for 7 hours and north-northwest 1/2 west for a little over 5 hours. The first section investigated in 1888 was in the equatorial drift between Tobago and Barbados, where 7 stations were occupied. The axis of the stream was found west of the middle or nearer the South American shore, and the average direction was towards the north. At none of the stations did the current set in the direction of the wind, although the trades were blowing at all times with a force of from 2 to 7. The daily variation was also here very pronounced, the average time of maximum flow occurring about 5 hours 56 minutes after the moon's transit. At 65 and 130 fathoms depth, the current, at 3 of the stations occupied, was northwesterly, at 1 southeasterly. The velocity at 130 fathoms was greater than at 65 fathoms and greater at the surface than at 15 and 30 fathoms. At all of the 3 stations between Grenada and Trinidad, tidal action was observed, with deflections due to local influences. The passage between Santa Lucia and St. Vincent appears to be in the line of the equatorial stream. At each of the 5 stations in this passage, tidal action was pronounced, the currents setting in and out of the Caribbean Sea at some depth. The daily variation in this passage reaches a maximum at about 6 hours 3 minutes after the moon's transit and a minimum when the moon is on the meridian. The currents entering the Caribbean Sea through this passage are but 100 fathoms in depth, but there is probably an almost equal volume flowing out below that depth. Between the Windward Islands, the currents flow generally westward, but tidal action is everywhere apparent. To the east of Desirade, the currents at all observed depths have a northerly direction, fluctuating between about northeast by east to northwest by north. In the eastern part of the Anegada Passage, the surface current flows into the Caribbean Sea in directions varying between south-southwest and southeast. But the submarine current down to 130 fathoms flows in a direction lying between north and east. In the more western part of the passage, the currents are more complex, apparently on account of the greater variations in depth in the vicinity of the station occupied. In the Mona Passage, no regular currents were perceptible. Between Mona and Puerto Rico, the currents observed set out of the Caribbean Sea, varying in direction from about west by north to east-northeast, except at 65 fathoms depth, where there appeared to be an inward flow. On the western side of the passage, near Santo Domingo, the direction of the currents was between south-southeast and southwest by west, but few observations could be taken on account of unfavorable weather. In the Windward Passage, on the western side, the currents from the surface down to 130 fathoms set in the directions lying in the southeast quadrant, and at 200 fathoms the direction changed to west by south. On the eastern side, the surface current varied between east-northeast and east-southeast with about 1/2 knot velocity. Variations in the directions similar in extent characterized also the subsurface currents in the middle and on the eastern side of the passage. The average of the observations at these 3 stations gives but a small volume of water passing in either direction. In the old Bahama Channel, at the station north of Cayo Romano, island off the north coast of Cuba, the currents at and near the surface set south of east. At 65 fathoms, however, the direction varies from about northwest to east. The deeper current of great volume flowed continually to the north of west with a velocity of over 1.5 knots at depths of 130 and 200 fathoms. Outside the Bahamas, to the north of Great Abaco, a slight current flows about northwest on the surface and down to 30 fathoms. At 65 fathoms depth, the direction changes to a point more westerly, and at 130 fathoms to a point more easterly than the set of the surface current. The maximum in the daily variation at this station occurs about 12 hours after the moon's transit. The observations so far as completed by Lieutenant Pillsbury furnish the most valuable data we have at present concerning the Gulf Stream, and it is hoped that further investigation and the analytical treatment of these observations will clearly develop the dynamic laws involved and lead us to a correct theory of current phenomena in general. Section 5 of National Geographic Magazine,